I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for the weekend just completed. Just ask that you'd be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I owe you a proof. Well, proof is probably too strong a term, but some larger explanation of what's going on with change of variables. And so I'm going to sketch to you how this works in n dimensions. So in coordinate change, the coordinate change in n dimensions would be something like we have some transformation which takes in u1, u2, un, and it outputs like x1 of u1 through un, x2 of u1 through un, and so forth, all right? Xn of u1 through un. So this is a coordinate change in n dimensions. And the thing is, we can look at this. Let me just kind of write this, So if we, consider a point, let's call it P, all right? Then we can look at T of, say, U plus, my bad, P of P plus a change in U, all right? And that's going to be equal to T of P plus what we'd call T prime of P times the change in U plus, well, higher order terms, according to the multivariate Taylor expansion. But what I mean by T prime of here is a little bit slippery. I'm actually talking about the Jacobian matrix, you see. So what we're actually looking at here is wherever T maps P, and then this is actually, the Jacobian matrix of T, which looks like, well, let's see here. Partial T, partial U1, partial T, partial U2, partial T, partial UN. All right, and of course this is all evaluated at P, technically speaking, but then times delta U1, delta U2, delta UN, right? So this is evaluated at the point in question. And essentially the point is this, that if you were to study, a little cube, little n cube, so n cube with n volume, delta U1, delta U2, delta UN, then that will get transformed by T to, a little n cube. Well, it's not quite a cube anymore, but I'll put a quotation on that, n cube based at P. So this n cube based at, let's say, based at P, n cube based at T of P with n volume. And this is the theorem. It turns out that the n volume of the resulting n cube, quote unquote, is given by the absolute value of the determinant of this, let me just give this thing a name so I don't have to write it all out again. Let's just call this thing the Jacobian of the transformation at the point P. So we take the determinant of the Jacobian of the transformation at the point P, that times, well, delta U1, delta U2, delta un. So if another way to look at this is if we rewrite this is equal to, if you will, delta x1, delta x2, delta xn. And so what this suggests then is that, dx1, dx2, dxn, we can think of as simply the absolute value of the determinant of this handy-dandy Jacobian matrix of the transformation at the point in question, all right, times du1, du2, dun. And then basically the point is, if I simply add up these infinitesimal n volumes over matching regions, then I get the same answer. And that's a sketch of the theorem. Now, let me just do n equals 3, where it's a little bit more perhaps understandable. So at n equals 3, we'd have, think about a little cube with like delta u on this side, delta v on this side, delta w on that side, right? And if we had my transformation, wherever it's going to, Jacobian of t at that point, and then I have to multiply by delta u, delta v, delta w. I'm going to bail on this. I don't think I'm going to. Sorry, guys. I'm not. My apologies. So at the heart of the theorem, though, is this theorem that if you transform an n volume under a linear transformation, then the determinant of the linear transformation times the n volume tells you how the volume scales. So, and then we just add up basically this, and so then we have f of x 1 through xn dx1 dxn. Let me just finish this thought, and then I'll give you a different way of looking at this, right? So this is over some region R, and my claim is that that's equal to the integral over, let's say, s of the function at t of u times the absolute value of the determinant of the Jacobian of t at u du1 dun. Now here, t of s is equal to r. So this is the s is how we would reformulate R, which is a subset of Rn, in terms of u1 through un coordinates. All right. So I feel like I need to finish this before I talk about my three-dimensional pictures, but that's essentially the proof, is that it rests on this result of really linear algebra, that the determinant of the linear transformation describes how it scales the volume if you pass a particular volume through a linear transformation. The basic thing about linear transformations, they take lines to lines, all right? So, yeah.
Is this going beyond 3 dimensions?
Well, there's a homework problem on 4 dimensions, so yeah.
Sorry?
There's a homework problem on 4 dimensions, so I mean, I do talk some a little bit about it. But
So,
how does that work? Same way. But, I mean, to calculate the integral over a 4-dimensional thing, we have to do 4 iterated integrals. Can I circle back to that later? I don't want to do that at the moment, but yeah.
Is that the hypervolume question?
Yeah, the hypervolume question's a 4 integral. But certainly we can do more examples, but let me finish this. So we could, if you look at, you know, let's get rid of the base point issue and just focus on like a cube, right? If I have a cube like this in W, V, U space, and you know, I'm just basing it at the origin to keep things simple, right? And you do T of UVW, all right, equals to a matrix, and let me call that matrix, I'm going to put A in the first row, B in the second row, and C in the third row. So I want to just talk about n equals 3 here for a minute. All right. And so I'm saying the formula, and you'll forgive me, I will stop the linear algebra in here very shortly, but I can't help but use linear algebra in this discussion because it is intrinsically guided by linear algebra. Like I could try to say otherwise, but it just is. So anyway, this is a 3x3 matrix, and this is a 3x1 vector. So when you multiply, the way multiplying these works is simply this. The formula is UA plus VB plus WC. Like that's how this multiplies out, okay? For those of you who've not had linear algebra, which would be like pretty much all of you, right? That's fine. So, all right, so like what happens when you think about feeding the, so this unit cube plays the role of S. And I said it's a unit cube, but it doesn't have to be, but like let's say that this cube has sides which are like delta V here, this is delta U, this is delta W, all right? So just like, let's say that those are the lengths of the sides of the cube based at the origin, right? So what happens when you feed this to T, all right, what kind of shape do you get over here in X, Y, Z space? So let's just sort through it a couple points at a time. So what happens, this point right here, right, would have been what? It's apparently delta U, 0, 0. So what's that? If I call this point A, where does that map to? It maps to this point over here, right? Let's say A prime. And A prime is what? Just look at the formula, right? I mean, we end up with delta U times A. All right, so this, if that far out. Let's see, another instructive point maybe would be this one. Let's call that B. B would be what? Looks like we've got delta U, delta V, 0, right? That's going to map over here to B prime, which would be specifically like, well, goodness gracious, my bad. I have lost the plot. So the point is, I don't know that A prime is on the x-axis. That's nonsense. Where is A prime? I mean, it depends on what A is, right? But if A is like, you know, let's suppose that A is like this, right? Then perhaps, you know, A is, this would be delta U times A, right? And if I look at this vector here, that's going to get mapped to, I don't know what it is, but delta V times B. All right? And let me just, I think it's probably better for me just to, it just dawns on me, I should look at the edge vectors, right? So this back edge vector gets mapped to that one, right? Delta UA. The green vector, which we could identify, excuse me, this is not the A vector, this is, what is that? That's U hat, right? Ah. The green vector is actually what? V hat, right? And the other interesting vector here would be the vertical one, right? And now I was trying not to say this has to be a unit cube. If it's bigger than unit, then the W hat is below that point there, right? But anyway, that maps to something like, I don't know what it is, like this perhaps, right? Delta W C vector. All right, and what happens if we trace out the whole story here, it's a linear transformation. So one of the things that means is that lines go to lines. All right. And so basically you can just take the vertices of the original cube to the vertices of the transformed cube. And that gives us, what does that give us over here? Parallel, what are they called? We talked about these before. It's been a bit, but a parallel what? Parallel pipette, right? So what's the volume then of this tilted? My picture's horrible, but anyway, if you can use your imagination, it's a parallel pipette with sides A, B, and C. Yeah, what's the volume of that? Absolute value of A dot B cross C, right? We could use the triple product to calculate the volume of the parallel pipette. But remember, there was another formula, which actually was the determinant of A, B, C. Right? Now, it's not just that. My bad. To be clear. Oh, man. Oh, come on. I'm sorry. I'll stop ruining everything I'm doing. I'm my own worst enemy today. So what is the volume of this? It's not just A, B, and C. It involves what? The changes of the input cube, right? So the volume would be the absolute value of delta U times A, right? Dotted with delta V times B cross delta W times C, right? But we can pull out the delta U, delta V, delta W, right? And then we'll just have the absolute value of A dot B cross C, which of course we could rewrite as the determinant of A, B, C times delta U, delta V, delta W. And so this is what's happening. If we feed a linear transformation, a cube, we get out a parallel pipette where the volume of the parallel pipette depends on the determinant of the matrix that defines the transformation. All right? But what I was pointing out at the start of today is that if we talk about a transformation of n variables, we can linearize the transformation, right? That, remember the multivariate power series? So like these are the first two terms, right? And so we can always form the best linear approximation to the transformation, and that's the only thing that we really need to consider to understand how that transformation rescales an infinitesimal volume. And then essentially we just notice that that volume depends on the determinant of the transformation, which in the context of a nonlinear coordinate transformation, that's the Jacobian matrix. And that, add them up, and that's the theorem in a nutshell. All right, so let's talk more about this Jacobian determinant. So just to be clear, for like n equals to 2, I would have t of uv is like x of uv, y of uv, right? So the determinant of the Jacobian of t is the determinant of partial t partial u, partial t partial v. Now I feel guilty for not putting vectors on everything here. Oh man. I have violated the terms and conditions for this course. Back to this board. It's going to take a second. Are you ready? Vector, 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 still vector, 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 vector. Made it to the middle board. Vector, vector. U is also a vector here. Vector, vector. 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 Oh, not a vector. Vector, vector, vector. Vector, 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 vector. Vector. Da! All right, I think I think I have fixed it. So in here, I try to, almost without exception, put vector signs on vector valued things, right? There are precious few counter examples to that, right? The only thing I can really think of off the top of my head where I don't write the vector was like the Frenet frame, the t, the n, and the b. Sometimes I don't write vectors on those, but okay. The point is it's vector value because you have both the x coordinate change and the y coordinate change. So the determinant of the Jacobian transformation is this, but we have a notation. This is also like, okay, so first of all, this is specifically x partial derivative with respect to u, the y partial derivative with respect to u, the x partial derivative with respect to v, the y partial derivative with respect to v. And we had a notation last time, which was just this, right? But I wanted to explain to you that it really is, in fact, the determinant of the Jacobian matrix of the transformation, which is the thing you need to form the best linear approximation to the map. So the question which inevitably will come soon after this is, are you going to test on any of this? And the answer is no, of course not. That's linear algebra, you know. But I think it's good for you to see it. And the trouble is when I try to make these statements in Math 221, I'm then confronted with the grim reality that much of Math 221 has not had Calculus 3. So like, where do we have this conversation? I don't know, but apparently here. So, I mean advanced calculus, I suppose, but if we have a three-dimensional transformation, UVW, right? So we've got x, which is a function of u, v, and w, y, which is a function of u, v, and w, z, which is a function of u, v, and w, all right, all. Then the determinant of the Jacobian of t is a 3 by 3 determinant. And, it's partial t, partial u, partial t, partial v, partial t, partial w, which is in fact the determinant of xu, yu, zu, xv, yv, zv, xw, yw, zw. All right, so this is the Jacobian determinant, which we have the other notation for, right? The slick shorthand. This is partial x, y, z, partial u, v, w. All right. Now I can kind of give you a summary of the change of variables theorem like this. Like here's a heuristic. Here's some heuristics for n equals to 2, right? For n equals to 2, the infinitesimal area, we can say dA, it's equal to dx dy. That's what the infinitesimal area looks like in Cartesian. Yes?
What's the
A
heuristic?
heuristic? It's a mental guide to remember a pattern. So a heuristic. Dx dy is the infinitesimal area element in Cartesians, right? But basically what I've tried to justify today is that we can take the absolute value, and there's another way to there's yet another way to justify this heuristic, which I think you might even believe more, which I'll do next. The geometric justification, all right? So essentially, we need this Jacobian factor to account for the fact that if we look at little, chunks of the plane that depend on change in u and change in v of a particular amount, the amount of area that subtends depends on the details of the formulas that define u and v, right? So with like polar coordinates, we saw that if you look at the polar sector, well, the area subtended by a polar sector depends on how far that sector is out from the origin, right? The farther the sector is out, the bigger, the bigger a change in area you get for a given change in theta, right? Because the further out the radius, the bigger the sector sweeps out, for a given delta theta. Now, n equals 3 here, the infinitesimal volume is dx dy dz in Cartesians, right? But in a generic coordinate system, we have to do this. We calculate the Jacobian determinant like that. And let me show you yet another way to derive the infinitesimal volumes. Perhaps this whole discussion has left you like just a giant question mark over your head. I get it. I feel you. I'm sorry that I did this to you. My apologies. Let me try to make it better. Maybe. The other way we can think about how to change the formula for dA in terms of another coordinate system is to envision the notion of a change in the coordinate holding all the other coordinates fixed. So like, if I consider, U1, U2, all the way out through UN, I can think about like D, the change along U1, which is going to be like basically some scale factor times du1. And, I'm sorry, this is not helping. Let me not do n dimensions. I'm an idiot. Duh. Let's think about polar coordinates, all right? I mean, just do what matters to us, polar coordinates. So if we think about a little infinitesimal change in the r direction holding theta fixed, that should be what? DLR, I would just say is just dr, all right? How about if I talk about a little change in the theta direction? Now, I want this to be the length that we get from an infinitesimal, displacement in theta holding r fixed. But what is that? That's r d theta, right? So what I'm saying here is, you got some point, right? We're fixing, for the first one, we're fixing theta, and we're going from here from r out to r plus dr, right? So this distance here is dr. The picture for the second one is I'm out here at a radius r, right? I'm at an initial angle theta, and then I'm sweeping whoop, up here to theta plus d theta, right? The question is, what's the length of this? What's dl theta? Well, dl theta is quite clearly r times d theta, right? And then as a general principle, dA is just this, like dA is dl theta times dlr, which of course is r d theta dr, which is what we derived from the Jacobian determinant calculation before, right? But as you can see, this is just geometric, right? There's no determinant in sight. I think this only actually works in as much as we're working with like orthonormal coordinate systems. We have to have that the coordinate lines meet at right angles for this to make sense. Otherwise, we'd have to do some more geometric reasoning. But this is almost the same thing for cylindrical coordinates, right? I won't draw the picture, but I think you can see that dlr is still dr, dl theta is r d theta, and what's dlz? Just dz, right? So my dv, as a general principle for, provided orthonormality, perpendicular coordinate lines, is what I'm trying to say. So dlr, dl theta, dlz, what do you get? You get r dr d theta dz, which is exactly the right formula. That's the infinitesimal volume in cylindrical coordinates. All right, so what's next? How about spherical coordinates, right? How do we find the... By the way, I mean, this whole discussion that I'm erasing at the moment, it begs a more deep question, which is, what on earth do you mean by volume of a four-dimensional solid, right? I'm not talking about volume in the sense that we're accustomed to it. I'm talking about the generalization of the concept of volume to four dimensions. So some people would say I'm defining hypervolume, and the thing I should say about that is to define hypervolume, or the generalization of volume, essentially is to define the determinant. The determinant and the concept of higher volumes are one and the same. It's not probably wrong as a slogan to just say the determinant is volume. That's again a slogan, but I mean, whatever we mean by the abstract notion of volume, there are some things that should be true for it, right? Like if you took the cube in four dimensions that has, length 1, width 1, height 1, depth 1, right? 4 spatial directions. Length, width, height, depth. It's the fourth dimensional spatial. I just decided to, use it in a separate way, so I have 4 separate directions. Yeah. I mean, we can't visualize it. It's four-dimensional. But whatever that means, surely the unit hypercube should have volume 1, hypervolume 1. So that's kind of a guide. Another thing is, like, whatever your notion of volume is, if you have like a hypercube where you have like 2 allegedly, separate edges are actually parallel, then that hypervolume formula, whatever it is, it should collapse to 0, right? If you take the hypercube and you double, it's a four-dimensional hypercube, and you double each side length, that should make the volume, the hypervolume of this hypercube increase by a factor of, well, how does it work for the cube? If I take a cube and I double the length, the width, and the height, what do we get? 8 times the volume. So for my hypercube, it should 16 times the volume, right? So there's some general patterns like that we can expect in the generalization, and if you study that, you'll be led to the concept of a determinant. The determinant, if we just take the determinant and we put in n vectors and n dimensions, that gives us the dimension of the n piped, which has edge vectors, those vectors. So for spherical coordinates, I can't draw pictures for that, obviously. Spherical coordinates. So my picture, I freeze theta and phi, right? I go here, which is at rho, and I go out here to rho plus d rho. What's the length of my little infinitesimal? It's just d rho, right? The length of the, if we just go from rho to rho plus d rho, freezing those. On the other hand, if I freeze, what do you guys want to freeze next? We'll freeze rho and which one? Theta? All right. What does that do? That puts you, freezing theta puts you in some sort of like, you know, what's the word? It puts you in a vertical plane, right? A half plane. And then if I freeze, I'm freezing rho, right? So I'm like here. And then so I have to, I'm sweeping down here. Still rho, but I've gone from phi to phi plus d phi, right? The question is, what's the length of that? dl phi would be what? The radius that we're sweeping is rho, and the angle subtended is d phi, so dl phi is rho d phi. All right? And then if we want to think about what's the other thing we can do? How about we freeze rho and phi, right? So we're stuck at phi, and we're stuck at rho. So that means that we're on some kind of circle like that, right? And so we could go, say, from, poor choice. Well, anyway, suppose I go from here, right, over to here, like that. Let me draw it. Let me redraw that. So here's my z-axis, and we're going from like here, which is at theta, over here at d theta. What's this? What's this radius here? What's that? Yeah.
Rho sine phi.
You say r is equal to rho sine phi. I mean, this is true, right? You guys know this, yes? So if we draw the picture for like an arbitrary point, this angle is phi, but this angle is also phi. This distance is rho, so we've got rho cosine phi over here. We've got r is equal to rho sine phi down here, right? And if you imagine the triangle down here, that angle's theta. So over here you've got y is equal to r sine theta. But by the way, that's also equal to rho sine phi sine theta. And over here, you've got x is equal to r cosine theta, but that's equal to rho sine phi cosine theta, right? These are the spherical coordinate transformation formulas. But more to the point, this is how the cylindrical and the cylindrical and the spherical radius are related. So this was exactly, so this r here, we're sweeping out, we've frozen theta, right? Frozen phi. So like dl theta is what? It's r d theta but that is actually rho sine phi d theta, right? So, all right, so we've found our infinitesimal length in the rho, in the phi, and now in the theta direction. To find dv, we simply multiply these. This is the geometric method. Again, it presupposes that these coordinate systems meet at perpendicular right angles. Otherwise, you'd have to think through the essentially the parallelepiped thing. Let's see here, d theta, d phi, dl phi. So what we got is we got rho squared sine phi d rho d theta d phi. And that's your formula for the infinitesimal volume in spherical coordinates. Yes, sir.
Isn't this the reciprocal of the scalar values when you're taking the partial derivatives to the chain rule for Cartesian coordinates?
So you're saying like these scale factors we found, the rho sine phi and the rho, they're reciprocal to the compensating factors we found for the chain rule for the spherical coordinates? Yes. And that's not an accident. We could derive, in fact, you can derive these factors from such considerations. But I wanted to do it geometrically at the moment, but you're absolutely right. So before I forget, you asked me what does a four-dimensional integral look like, right? And so let me answer that the same day you ask it. All right. I should finish this though. How do we calculate this volume from the? Oh goodness gracious! What am I? In example 2? What would partial x, y, z, partial rho, phi theta? Now, notice, by the way, that I'm switching it up from the notes. In the notes, I have calculated partial. I've got the phi and the theta switcherooed, you know. So what's the determinant of? So x rho, y rho, z rho, x phi, y phi, z phi, x theta, y theta, z theta, right? So the question is, how do we? I got it. It's fine. How do we calculate those determinants? All right. So the rho partial derivatives are super easy, right? That just gives us like cosine theta sine phi, sine theta sine phi, and cosine phi. That's my first column. Now the phi derivatives, I've got rho cos theta cos phi. I've got rho sine theta cos phi, and minus rho sine phi for my last entry there. Now theta derivatives, I've got minus rho sine theta sine phi, rho cos theta sine phi, and this is my favorite one of all, 0. So if you're not understanding what I'm doing, I'm just differentiating the spherical coordinate formulas, which you absolutely must know if you're going to be successful at what we're doing this week, right? These are mission critical. We need to have these sort of at the tip of our tongue, know those. Now we have to calculate this determinant, so let's do it. So we've got cosine theta sine phi times 0 plus rho sine phi times rho cos theta sine phi. minus rho cos theta cos phi times 0 minus rho cos theta sine phi times cos phi minus rho sine theta sine phi times minus rho sine theta sine squared phi minus rho sine theta cosine squared phi. Oh, hey, that's nice. Notice that last one of our favorite things. I mean, this we can rewrite as minus rho sine theta times sine squared phi plus cosine squared phi, right? All right, so let's see here. I've got a rho squared cosine theta sine squared phi here. Plus rho squared cosine squared theta sine phi cosine phi. Hold on a second. I gotta be careful. Sine phi cosine squared phi. All right. And then over here, I've got a plus rho squared sine phi sine squared theta. That's from this business. Aw, man. Something feels off. Oh! Let's see here. Oh, look at this, guys. There's an error right there. Do you see it? I got cosine times cosine here, right? So that's a cosine squared there. And I've also got how many sines? 1, 2, 3. That's a sine cubed here. All right, so let's finish this thing. We've got rho squared, factor that out, and I've got, I got a sine phi, I factor that out. Then I've got a cosine squared theta sine squared phi plus cosine squared theta cosine squared phi plus sine squared theta. See what happens here? These two guys simplify down to just cosine squared theta, because we can factor out sine squared plus cosine squared phi. And then we've got cosine squared theta plus sine squared theta, which, lo and behold, we've got rho squared sine phi, which is what we just derived by geometric methods. Right. So you asked me, like, how would we do a four-dimensional integral? The answer is basically by the same means we've already been doing. Like, here's a horrible one. X squared plus y squared plus z squared plus w squared less than or equal to 1. You could do integral from -1 to 1, integral from the square root of 1 minus w squared to the square root of 1 minus w squared, integral minus the square root of 1 minus w squared minus z squared to the square root of 1 minus w squared minus z squared, integral square root of minus 1 minus let's see here, w squared minus z squared minus y squared to the square root of 1 minus w squared minus z squared minus y squared. And then this would have been d, apparently, goodness gracious, I guess I did x first. And then, oh man, now I gotta think. Well, hopefully this is right. So this would be like the 4 volume of the volume bounded by that inequality. I should probably still put some quotes on this because I'm hurrying. But we keep doing the same thing we've been doing. We just add another set of inequalities. I'll try to work one where I actually work the number out like next class. I'm sorry, guys.